Okay, so we can start for this third lecture.
Okay.
The Zoom?
Yeah, I don't know, but I guess anybody knows. Who's the one who knew?
Huh?
Who's the one lecture will be
Is Yom the one who's using it? So is Yom the one who's figuring it? Why don't we next week do something? Oh, to figure it out. Yeah. I'm just saying for next week.
on probability.
So what are we supposed to do?
Discuss the involved measure. That's it. So to solve it, you have to consider what we call cyclic criminals on their relation with probability. Or maybe something for the maybe since there is mathematician. So just to recall that we look at the open case that we want to solve. So there is sides and sides. So there is open term corresponding to an Hamiltonian DH. Look at this CD. Don't forget when there is a injection and extraction processes. And the way to solve it is by studying the two-point function, which I call Gij. This is a quantum expectation value of T I direct Cj. That makes sense. So first, I will need to use graphical notation. That each element Ij is represented by an oriented link between I or maybe Gi. Okay. So when we look, want to compute the invariant measure, we would like to compute E of monomiality notation. To each monomial, that will correspond to the graph. So I will either talk about monomials or the graph. Okay? No, Ian? So this matrix S satisfying SG. So there is some SG. I discussed last time, which is something which is there is a drift, and then there's something with the GW. So it's always linear in G. So when you want to look at the invariant measure, you have to impose that D. So for the invariant measure, D of G of 2. That's the same thing as E of D of G equal 0. And it's the same thing. Where you use Ito calculus to do that. What you get obtain, because it's linear in G, you obtain a linear system for a given order of the monomial. that's Pj, so Gg with P entries J. So you get a linear system. On the expectation value in the value. Right. What's the expectation? Then you just have to solve the linear system, which becomes bigger and bigger as P increases. And as I said last time, if you compute for P equal 1, which I will draw like that, there is only G, Ij. You find that it is NA, NB, X minus 1. Not the two possible. X and B minus 8. So this will correspond to X equals 0. This will correspond to X equals 1. On the variable I use, the X, that's in this I, X is I over N, and this is value when N goes to infinity. And NA is defined as for step in terms of the injection extraction parameter. Okay? So NA should be something like alpha plus beta, where alpha is the injection rate and beta the extraction rate. And NB is gamma or gamma content. Gamma.
Suppose you also have the result for infinite.
Yeah. So, and then so that's just for so it is equal to G I. Then I told you compute G and J, this is 0 if I. And in general, the E, so that's for people like. So in general, the expectation value of a graph come from 0 only can be non-zero. Only for Eulerian graph. And the Eulerian graph means that if you look at a vertex, the number of ingoing arrows should be the same as outgoing arrows. Okay? What does it mean? It means that so the ingoing corresponds to if you use the matrix as what the ingoing corresponds to the ingoing states. So G is a actual. You can view V as the element of V star times V. So that's the ingoing one now. That's the ingoing out. That's the outgoing hours. Okay. So it means if you inside the monomial, if this is the vertex J, you should have the same number of J with the indices is in that position than with the J with indices in that position. Okay. So that's due to that's a consequence. This follow from the U1 to the A invariance. Because when you have this Hamiltonian here, you can change Cij by any phase. Cij, Cij back. Okay, you act with the U1 invariance on Cij. And this will, if you do this modification, you will have an extra phase here that you can absorb in W. So in law, they are equivalent. Okay, so there is this equivalence in law invariance in law. that's why for this is an example that will be graphical representation like that. That's why it's 0, because it's not a variable.
Can you write down the ST for G just so that we, for completeness?
I gave it last time, I forget.
Yes.
Do you want the exact expression?
Well, I mean, you know.
I don't have it here.
Fine.
You don't need it.
I don't need it.
No. So you know there was two parts. There was B coming from exponential minus G, GH, G exponential plus BH, minus G. So that's the first part. Okay. And this corresponds to a reshuffle of the, it's a noise part. And then there was, so it's a, like, there's two parts. And then there was the boundary terms. Okay. Which I will write a mistake if I write it. Which correspond with depend on this parameter. So if I look at p equal 2, what you compute, for example, this one, you find that it's delta n over n x y minus y, so x less than y. If this is x, or if you want I over j, so it's I of x is I over n, y. Okay. Then okay. And you can go on compute. And then you can compute the other one, you can compute.
What is it?
What's that delta NR? Right, I will write delta N and B minus N. So you can compute this kind of things. You can compute this one, the connected one. You can compute that one, connected, and so on. And they are different. Okay, and they don't scale the same way. This one is of order 1 over n, whereas this one is over 1 over n squared.
So just to make sure, the second one means GII squared and the third one means GII, GIJ?
Yeah.
Okay.
Hey, exactly, that's the notation. Okay, connected. Good.
How do you compute that? So for
It's a linear system. You ask, so what is computation? We are done with Tony J. So it's just a linear system, so it's easy. We compute up to the 3. 3 becomes a bit more complicated.
Yeah, system with a inhomogeneous.
It's a linear system, so you look at all the possible moments of a given order. There is a surdetermined system, but you can find a solution.
With a linear system equals some constant part, or
No, 0. Big
why
matrix.
is the solution not 0?
Huh?
Why is the solution not 0?
Ah non, the constant part to
Okay.
Just see this.
means connected. Ah, so in math, it's a second cumulus.
Can you quickly see the exponent without having to solve the whole?
What?
Can you quickly see the decay without having to solve the whole equation? Is that easy, or does it come from subtle cancellation?
Then it will be a consistent solution. That will come from consistency of all the equation.
Right, but I mean, the fact that one of these decays like 1 over n versus one of these decays like 1 over n squared, does that come from the fact that in the SDE, the second guy is weighted by an additional factor of n? Or does that come from some very subtle cancellations that occur?
That comes from general structures that we assume for all higher orders. So it's not hidden in the SDE, it's hidden in the linear system you get from the SDE.
Yeah, that's what I meant. I mean, from the linear system, do you
Yeah.
see it weighted?
Not
out?
directly,
Oh, okay.
but we will see that it's consistent with the linear system.
Okay.
That's what we mean.
Okay. There's a unique solution to your linear system. There's unique solution.
Yeah. At least, yes. So P equals 3. I continue, and then I stop. E. Then you can compute all the other one. Okay. So this leads to general claim. The claim 1. Loop, the one which is from a loop is the one which is the leading term. Dominant is the leading. Which means that the one which matters is this one, where you have P point, so you have P point and P insertion of J in a cyclic way. So this is E of G1 I2 GIP I1. Okay, and that's the leading one. The leading one for up to now, assume that the indices are not all distinct. Okay, on the order of that, it's scaled like 1 over n to the p minus 1. Okay, so that's what you can observe in the example I gave you. Okay. And when the indices, when you pinch it, it's continuous. So this is like to define. So what you have to compute E of E x1 xe so this is of order P and T. So that's what we call the loop expectation value. So you first compute them for all the I. All. Well, once you know that, so all the other terms, all the other cumulants are subleading. For example, this one here, you see that this one is of order 1 over n, whereas this one, which is another cumulant, is of order 1 over n squared, subluminant. And this one, which is obtained by shrinking this one, is of order 1 over n, and actually this value is this one with x equal 1. Okay?
This function is cyclically invariant.
No. So then you have to be that. So solving QSEP, we want to find this solution, this function. Okay? And here you see I have it's cyclic invariant, but not gravitational. It's cyclic invariant, of course, but not. So then you have to be careful about the order of the point.
I don't understand. So what is the pinching?
Just
You
I identify these 2 points, and then I fuse. I get a bubble.
okay, but then in the definition, why do you need the IK to be distinct?
Because this is a cumulative, because here I put the expectation value. If I, okay, otherwise. Yeah, okay, here it's a cumulant, okay? So the cumulant will be continuous, but not the expectation value. Okay. So here I put the expectation value. Since all the indices are distinct, I can put the cumulant if I want. So instead I could put C, because the relation between moment and cumulants, you know the formula, which is somewhere partition. Unless you have the total partition, the other one will be made of blocks, which will correspond to non-aligned cars. So they will be zero. Okay. But so I want to compute that, and so they satisfy. So what I will describe is they satisfy some relation due to when you impose the stationarity, because you do that on the invariant model. And okay, and free probability comes from this equation. So the third one is the claim. I will give you the solution, and then I will explain a bit how to do it.
Wait, so would I be correct to understand like Gij, it's usually an order 1 over root n, but then there are many cancellations when they look at our cumulants.
Say it again.
Gij, when I is not equal to j, it's usually an order 1 over root n, but then all these cancellations will make these cumulants go slower power.
Yeah.
Okay.
Which is exactly for to have such a scaling.
Yeah.
Ensure that you have large deviation function, because this ensures that you have something like if you compute exponential of trace of aj, then I have to be what this is normalized trace. So that will be exponential of n, some function of a. Then I have to normalize the trace 1 over n. You know, it's like a large deviation function.
But not just age, you can multiply many times g to the n or something.
Huh?
Like, you can multiply g by itself many times, no? Somewhere? Because this is not the full thing, right?
There's an n on the other side.
Huh?
It's not 1 over n. It's
N, yeah, yeah. That would be a mistake. So this ensures that there is a large deviation function as always. So it's why you don't have to scale some power with a small parameter. So the claim is Gn. So you consider let 0,1 with the equal to the Lebesgue measure. Okay. E of x is the characteristic function of the interval 0 from x. Okay. Which means a little pi. This means that f of b x1 is x. P is the minimum in x1 xp. And gp of x is the cumulant of the variable x1. So this gives a complete solution of the problem.
I guess I'm normalizing so that n equals 0 and n equals 1 or something.
Ah, yeah. But different NA and NB are often by shifting.
Yeah.
So, so I will tell you the history of the program a bit later, but now I want to show some formulas how to find it, or maybe I should have done it differently in different order.
We're going to define the equivalence.
Huh?
You're going to define this equivalence.
Yeah. So an example, complete equals 4. Example was actually found before this was proven, so we will not remember. We don't know them by heart. We choose x1 less than x2, less than x3, less than x4. We put it 1, 2, 3, 4. That's n minus, so it's 4 points, so it's at n minus 3. There is an x1, should vanish. And there is 1 minus x4, it should vanish at x. X4 equal 1. And then there is the polynomial. 3, x2, minus 2, x3, plus 5, 2, x3. But if you choose, it's the same order, but you change two of them, any which one I should change, this one. So I could have given the example before the main theorem. So that's what you find. Again, we found them without knowing this theorem at the beginning. So what you notice is that so they depend on the order. They are cyclic invariant, but not permutation invariant. Looking from 4. So you always factorize, so it has to vanish at x equal 1, which corresponds that there is no fluctuation at the boundary. When the other one, the other boundary also, there is no. So the reservoir fixed. Fix the thing, so there is no fluctuation. So these are always integers. So if you change even x into minus x, the coefficient belongs to n. And there is a mini combinatorial aspect related to that. But for CB, she's not here, but combinatorial aspect, for example, if you set all the x equal to minus one variable, all these polynomials are the same, so you have some polynomial for your p. And this is this polynomial is a genetic function of the number of faces of a given degree in the associated, something I don't know, but you just look at on the net what they mean, and that's what they mean. Okay? So these are genetic functions, combinatorial genetic functions. So the way to prove that, so you have this function, so G is loop expectation value. And minus 1, that we should call Gx, x1, we call Gx. And they satisfy some condition by stationarity, okay? Because I but you see, when you write this function, you have a conflict between two possible orders. So you have the order in the loop, and then you have the, so there is one order here. And then you are on the line, they are on the line between 0 and 1. And you have another order here. And they could be not the same, which is what I have written here. Here, I choose an order on the line, and depending if this order was the same or not, and we have different answers. Okay, so the way to write the stationarity condition, so depend on which convention you choose. So I will first choose a fixed ordering on the line. So 0, x1, xp, 1. If you fix that, so you fix on this line, so then this will be indexed, depending on the ordering, by sigma, which is a cyclic permutation. Okay? Because I can put x1 here, put x2 there, x3, and so on. Okay? I can choose where to put it. This defines the cyclic. Okay. And then there is some condition. We just follow by looking at the stochastic differential equation. So the first one is thermal energy, which is diffusion. Thermal energy dx p square g sigma is equal to 0. Okay, so when they are far away. Okay. So that, by hypothesis, we just made it local. We didn't prove that it has to be. We just impose it. Okay.
You cannot prove.
We didn't try. Just has to be local. If it was not true, it means that the property will not be local.
The function you wrote here should satisfy this.
Yeah, so it's a polynomial of degree 1 in each variable, which is okay. Then there is a boundary. G sigma at x1 equals 0 is 0. G sigma at xp equals 1 is 0. That follows also from the. So there is no fluctuation at the boundary. That implies by the black inset. Then there is some continuity. Because when you look at the equation, the SD has been white, they exchange the point, the nearby point. So then you have a continuity which tells you that if 2 points are nearby, okay, at contact, continuity at contact, let's say. Okay. Somewhere here I have xj plus 1. So sigma at xj equal xj plus 1 is equal to the self where you have permuted the 2 points. So it means that what you compare here, you compare something which where you have xj here, xj somewhere, x1 here, xg plus 1 here, and there is many points at different. Okay. So I exchange the two. My cycle go like that. So tau G is a permutation between the two. So I compare this one with the one where I compare xg plus 1, xg. And they should coincide, okay? But now there is an interaction term, because there is nevertheless like a gas ball. And you have to take the derivative of the two, sigma. Now the derivatives are discontinuous. There is some discontinuity in the derivative. And they are linked to other loop expectation value. And I have to define what is sigma plus and sigma minus. So here I have sigma, the big sigma. So, okay, so that's in white, this is sigma. And sigma minus, so I turn clockwise. So sigma minus is something like, I go clockwise up to xj, and then I go back on the loop, but avoiding xj plus 1. So that's sigma minus. And sigma plus does the opposite. Hope I didn't do a mistake. And sigma plus is that one. I start from with the same thing. Something, just exchanging the two. So I go along the loop, and I just avoid one of the points, but keep the other one, and then the other. So I break my cycle in two pieces like that. Okay. So this give me define two loops which are smaller. Okay.
Minus is a cyclic permutation.
Yeah, but of smaller set. Not it's not a cyclic permutation on 1 to p. It's a cyclic permutation of the points which are here.
But then it's evaluated at the points from x1 to xp, or?
But you see, since it's linear, when I take no, so this one will become, I take one derivative, so it's independent of xj. It's linear. It's evaluated at right. Dependent, no, it's evaluated at this point, dependent on that. And this one will depend on this variable. Okay. So now it's a triangular system on P that you can solve by recursion. Okay.
So this fully determined.
Yeah. So with Tony, what we did, we completed the first few. We proved that there was a unique solution. We have an algorithm to prove it. We have generating function to generate solution. And then the proof, so then I gave the problem to Philippe Lian, who is a combinatorist, and he proved the formula with the figure. But then now that's a combinatorial proof, which I will read. Starting from what we did with Tony. Because we show how to manage this equation and how to propose an algorithm to solve that. I'm going to prove. So then now we have another analytic proof, which I will describe. Also based on free probability with Ludwig. So of course, it's not a complete proof. We assume that from the start. But once you assume this relation, then it's unique. And the way we find that is that we start with a discrete model. And as I said, it's a linear system. But then you have to look at this system carefully. And sometimes you encounter, we get this formula by assuming the scaling I said for the loop, and assuming that if you have disconnected loop, you factorize. And this is how we get this factorization into smaller loops. Okay, so it's not a complete mathematical.
So the continuity is kind of not obvious, right? Because it's two different limits, order of limits. Because you take your eyes to be first far from each other when you take large n. And then you kind of bring x near to each other, but you would start with the two indices percent before taking large n. Different things.
Yeah,
but we'll check.
I mean, I'm sure that there's another limit because so the way we prove, for those who like topology, algebra, and so on, there is maybe another approach. So the way we started is we study objects which are, I don't know, a form anything, we call it A, I, J, P, or J plus 1, let's say. And this is, then you have to look at something which is well, they are connected, forget. So then you have to look at objects like that. So you have a closed set of equations with anything. Since there are no types, the equation, you get a closed set of equations of objects like that, and the move are just the SG involve only local nearby point because the jump were on sites which are just nearby. On the basic object, which seems to indicate that there is another third proof different from what we have, which is linked to Young-Baxter, is if you look at the SDE of an object which is anything B at a point G, you take the derivative of that. When you do its Ito contraction with something at G plus 1, that will be, there is a minus, but you correspond to a reshuffle of the arrows. That's the main equation which lead to this kind of intercontinuity to the equation. You move them. So this seems to indicate there is something probably linked to topology algebra, which will give a better proof, but I don't. So again, the way so that's what we did with Tony. Again, we had the generating function to solve them. It was clear that it was combinatoric because you can, some of the generating functions are just the one generating function of Catalan numbers, but the external also. So it was clear. Then Philippe Bian solved this equation first by some combinatoric tool by mapping the problem to some graph, which I forget the name, and then realized that it was like probably free cumulant. And then now we have an analytic proof, or maybe I will just give you the hint of the analytic proof.
The proof of what?
Proving that the solution of that are the free cumulant of the one I said. Any questions? Because there is too many equations now.
Not equations.
Huh?
They're not equations.
There's no equations? It's full of equations. That's
Is there a way to deform the model depending on some parameter in such a way that the current of G sigma would not be an eigenfunction for Laplacian with 0 eigenvalue, but something else?
so you want a constant here, the function?
Laplacian of G equal lambda G, where lambda would depend on parameter, maybe parameter Z1, Zn, or, but there are other deformations that respect that structure.
Maybe, I don't know. Okay. We have tried to generalize the model where we put inhomogeneous hopping rate along the chain, maybe a bit along the, but then I think we cannot solve it that way.
The set neither.
Huh?
Neither the set.
Neither the set. Okay. So, I will not do completely the proof. So the first step is the role of non-branching partition. So what we want to compute is the product. That's a moment. And as you know, the moment can be written as the sum of our cumulants. So the variable here are the AB, so the variable are the variable, which is the same thing. And the sum, the relation between moments and cumulants is the sum of our partition. So you have to sum of I, other partition if there is P of P. And this defines the cumulant now where we call it CP. And the partition is made of different blocks. So if P is a set of blocks B1 to be a kernel of P, we'll give an example for, then CP CP is the product of the cumulant for each of the blocks. That's a general cumulant. And what I will argue, but maybe I will do next time when we discuss structure function, is that not all partition contributes. Okay. So we'll just give an example, not discussing in detail because I will do it next time. So for example, P, first I will do P equal 2. Okay, P equal 2, not that. So there is two edges, okay? So there is two possibilities. There is a full set. So this one, I will call it, I will put a link to tell which belong to the. So there is a full set. So maybe I call that 1, and that's 2. So there is two partitions. It can be either there is only one block, so there is 1, 2, that's one partition. And the other partition is made of 1 and 2. Okay. So it means that it's I, J, this is cumulant of G, I, J, G, H, J, plus the cumulant of G, I, J, J, I. That's the second cumulant, that's the first cumulant. Okay? Just relation between it's the variance between the moments. Okay? So that one. So that we know that it's scaled like 1 over n times gxy d2. Now this one, by U1 invariance, there should be a delta function by j. Otherwise, it's 0. Okay. And then it's g1 of x and g1 of y, or if you want, y equal to x. But this one, in physics term, but I will tell you what is the mathematical term, is equivalent to the delta function in the limit with the factor n minus 1. So it's the same thing as n minus 1 delta x, a delta function. If you don't like that, that's a physics way of doing, you look at E of a trace of this product of G with the diagonal matrix G1, G with another diagonal matrix. And if I were doing GP, I will do that. And because you do the trace, you have to sum, and you will see that this takes care of the factor delta. Okay. Because there will be one, here there is 2 indices to sum, where here there is only 1 indices to sum. Okay. So this one is like n minus 1 times G2xy plus delta xy G1x G2y. And this corresponds to when I have my partition. This is this partition here. And here I have two different partitions. But then I have to impose a delta function. Okay? So that's for 2. You can do for 3, for 4, whatever. And then there is a general statement, which is if you just by assuming UN invariance, the scaling means like that n p minus 1 e p I1 I2 IP E1 the sum over the non-crossing partition function of some function GP, the GP, times delta of x. And then I have to tell you what is the non-crossing partition function. So for p equal GP, p equal 4, so I have these 4 things. So I can look at all the partitions that there is like this one. The full partition, that's the complete partition. Okay. All the same. Then there is one where there is a triplet and a singlet. Triplet and then a singlet. And then there is a permutation of that. Then there is one where there is doublets. For example, this one, plus this one, okay? And then there is another one which is when there is 2 doublets, they cross, and then there is maybe the one with all the singlets. Okay.
Can you explain a bit better your drawing?
Huh?
Can you explain your drawing?
So my set is the edges. Okay? When I look at partition of the set of edges, and I draw a line when the partition is made of blocks. Blocks means that you have a set. Partition is made of subsets. And each time the edges belong to the same subset as this partition, I draw a line joining the edge which belong to the set. Okay, to the block. Here there is only one block because this is the total partition. Here the partition is made of 2 sets, a singlet and a triplet. Here the partition is made of two sets, each of 2 doublets. Okay? And then is 2 doublets, and here it's made only of the singlets. Is it clear now, the notation?
Can you do an example? Like what is the left side is supposed to be G1, 2, 2, 3?
Yeah, so this is E, GI1, I2, GI2, I3, GI3, I4, GI4, I1. And with I1,
Yeah.
I2, I3, I4. Okay?
In the first, say the first green term, what would that?
This term means the loop expectation value. So that's what I was going to define. Because G, in a way analog to this one, this G, P, the product of the block will belong to P of G of the block. Okay? Each of the block is made of this one. Okay? So this one actually will be the function G corresponding to that. Now this one, if I was computing, so here it will be cumulant, so that will be the cumulant of G, 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 okay. And no constraint from the UN invariant. Now this one is E of G, cumulant of G, 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 cumulants of G, okay? But this one, for example, there should be, which one? There is a delta function from that, by U1 invariant. So these two indices have to be equal, okay? Now here, I do the same thing. This one will be V of G, a cumulant of G. But by U1 invariant, these indices have to be equal. Okay? Same thing here, they have to be equal. Okay? Here they all have to be equal. And if you look at the scaling, they all this one all concept. Here there is too many delta functions. Because if you look at it's again E, but when you look the cumulant of two doublets, but if you look at the U1 invariant, it imposes too many delta functions. Sometimes the scaling is subleading. This one is subleading in N.
But can you, where does delta function come from? What does it mean, delta of pi star x?
Yeah, that's what I am going to try and explain that. So you see in all this graph, so again, the crossing one is subleading, there is only the non-crossing one. When you have a non-crossing one, you can always insert it. So this is a partition function, partition of the edges. You can always insert a non-crossing partition of the vertices, just in between. So the yellow one is what is called pi star. The green one is pi, and the yellow one is pi star, so forth. Which means that just take care of the U1 invariant. So if you have a big cycle with some partition, non-crossing partition, so it has to be non-crossing. That's a non-crossing one, for instance, okay? So that's pi. It's made of 1, 2, 3, 4, 5 blocks, okay? And then there is a non-crossing partition of the vertices, which is that one. If you want, this one is alone. One is alone. Okay? That's pi star. It's called the École radial. And so the sum here, if you look, there is all the cumulants related to partition and the delta function from the U1 invariant coded by the École dual. Okay? And because you have no crossing partition, there's a link with the field probability.
You can show that our crossing partitions have subleading order.
Yeah. For any order. Then you can do the counting.
Yeah, it's clear as an example, but in general, there's a challenge.
This has something to do with planar graphs also?
It's not the same graph that you do in matrix theory, but it has to be, but it's not exactly. Okay, so I think this is a beautiful formula, actually. So that's why you can compute with free probability. This is. Any question on maybe next time I will do the computation. Yeah.
You will explain why it's subleading order? Or?
Yeah, I will explain next time.
Okay.
Because it goes into the gene. And then the proof that we have is so then you have equation for. So if I so this one. So from the SD, from scaling limit of the SD, of course we get differential equation for the thing. So we have an equation even for in time, if we scale in time, dt to the power of x is equal to something that we do okay. The minus is relative to 1.
What is S? What is the subscript S?
S is just to, that's the definition. Okay. I could call it S because it's not the cumulant, it's the expectation value, and there is singularity. So you have an equation just from the SD, from the move, you take naively, it's like a delta function, but it's a bit different. You have contact term, and we have the same things about cutting this. This one is actually to a loop, and you cut the dive xi, xj, and you cut it. And this gives you this thing. So that's equation of motion. You were asking if there was a time. You can look at the time evolution. So that's the time evolution. It's the time. So if you look at the steady measure, you have to solve this equation. Then you define, which is a bit bizarre. So you know that G will decompose like that. We define phi x without the delta function. So we just erase the delta function. Then you prove, that's a difficult proof, that it satisfies the same thing, but with a delta x I, delta x j, phi minus phi plus. And this, okay, then I will tell you what is the interpretation. And then you check. And then that's phi x equals the mean of x1 to xt is a solution, is a steady solution. Okay. With a good boundary condition, which I mean not discussed, with appropriate. And knowing this function, so pi mean is the expectation value of something, and this formula is the definition of the precumulant. Precumulant, instead of summing over all the partition, you just sum over the partition, non-constant partition. And that's the definition of the free cumulant. So this in mind that the G index pi for any partition pi is a free cumulant. And since this is the product, the loop has a free cumulant. So that's the proof of this steady measure. So of course, we don't have a good interpretation of doing that. So we did that because we knew that we had to extract that this one has a simple interpretation in terms of probability measure. But it's a bit bizarre that you just erase the delta function. This kind of sum in free probability has a meaning when you have three variables, you have a sum over naturally pi and Crever's dual.
Can you repeat the last part? G pi is what is free equivalent of, and phi is moment.
So yeah, so we start with that, okay, and we know the equation is satisfied just from the SD, okay. And because of the scaling, we know that it decomposes like that. And you can always invert. So we just from that we can extract. So there is a relation between this object and this object, you can extract that. And you can prove that if this is satisfied, when you define phi, you get this equation here. With the main difference that you move the dx. So it's a long proof done by
What's the role of this mean of x1?
And then what we prove is that you look at the steady solution. Okay. And then the mean is a steady solution.
But this is related to your Lebesgue stuff? Or?
No, since it's that you can interpret as a moment, but it's a steady solution. And from that, because when phi is the mean, you learn that the G pi are the free cumulant of the measure for which.
Okay.
So this implies this phi equal mean that G pi are free cumulant. Of the variable X with respect to the ring. The most difficult proof is that go from
Then can you, I guess you can calculate this F of A, which you were writing.
Yeah. Right, I will maybe discuss next time, because then what you start saying that is that you have a general structure for matrices. So this leads to the theory of structure matrices, because here you have quantum matrices with the same scaling as you have for R or bits or whatever. But now the expectation value depends on the position of the indices. So it means that the matrix has some structure. And that leads to what we try to develop.
Since you have the measure for which, these are free cumulants, I guess you can write the probabilities.
Yeah, you can just write the genetic function, you can write a number of things, but
The fact that you can move from step 1 to step 2, you can move the delta function from inside to outside of the derivatives. This is something not
difficult.
and it's related to the combinatorics of.
Yeah. So there is a combinatorics somewhere. So in Philip's proof, there was combinatorics related to this, either to probability from the beginning or from the trees. Here, the combinatorics is hidden in this move here. It's a very long proof, actually.
Is there a way to guess that the phi t here or the cumulants of
No, that's
variable that satisfy dt?
but here you see that they are invariant by permutation. So they are cumulant of some classical variable, which is a bit bizarre because usually free probabilities for non-commutative variables. Here it's we are dealing with free cumulant of commutative variable, and they are not free, variable. But what you see, you don't have these invariants with respect to permutation. So if they are cumulant of something, it's a non-commutative variable. We don't know what they are. If we knew, that would be a way to formulate directly in the continuum, at least some part of it. But we don't know the process which generates this object. If we knew, that would be.
What did you mean by the last statement? If you knew, then you'd be able to formulate what in the continuum?
If there was a process for which this will be the measure, then we could reconstruct everything from that process. Because G, or the cumulant of the expectation value of G will be reconstructed. So, but this process has to be non-commutative because unless we did mistake, this one is not invariant by permutation, it's cyclic invariant. And well, it would be good to have it.
So it becomes invariant only in a large time limit? Or?
Yeah. And if we didn't know that there was a relation with free probability, we will never make this passage from here to here, erasing just the delta function, which is not natural to do. But okay. And for example, just to finish, if you are interested in set, just so we know all the. I told you that set is included in Q set. Actually, I said before. So it means that if I compute the IP in set in the steady measure, okay, it should be computed in terms of this data. So we know that this one scale like n to the p minus 1. If we take all the I different, and the formula is that this is the sum over minus of the p plus 1, sum over sigma over the symmetric group up to Z2, which corresponds to inverse of G, where you have acted with. So you take something, you start with the cumulant of the expectation value, which are not permutation invariant. You sum over the permutation group, they become permutation invariant, which has to be for that, and you get the answer. And that's from that you get large deviation function I mentioned the formula. And that's full for the fixed error.
Why? It's supposed to be the expectation value of the QSEP.
Yeah, you start from you start to write that in terms of QSEP, the mean of QSEP, you use this theorem, you look at what is leading term, and you get that.
Some of the permutation, they come out from the.
Fixed error.
This polynomial.
So it's why in QSEP, in a hidden way, there is this combinatorics, so it's related to associated rules. But it is hidden because you have to sum over the permutation group.
And these polynomials, they were known?
No.
Because they also can be expressed using the matrix product on that.
Ah, this one are known. Yeah. I don't know if they were computed up to that. But of course, yeah. They were, this one were not. What I mean is that this one, this J, were not. No.
Okay, thank you.